Okay.
Okay.
Yes.
So, hello everyone. Pleasure to have you here for this this second set of Simon's tutorials. Today we'll have two outstanding lecturers giving talks. One of them is still flying. The other one is here and made it just on time. So we're quite fortunate.
Oh, was he trying to get back from Aspen?
Yeah.
Oh, I'm so glad. I'm so glad I didn't go there. Yeah.
So, so the first speaker today will be Andrea Liu from UPenn, and she'll be talking about. Her talk, or the way we've tried to structure the talk, is that Andrea's talk will be a bit more general about jamming, and Mathieu's talk will be more specific about one subset. So that's why we were hoping that they'd show up in the right order for giving the talk. So pedagogical thinking that went into it. And without further ado, please, Andrea.
Okay, thank you, Patrick. All right.
Maybe I should say, please feel free to ask questions.
Yes.
This is, speak loudly and clearly, but this is meant to be a tutorial, a discussion. If you don't ask question now, you'll never know. So.
Okay. Yeah, so I tried to structure this talk so that I would not be covering things that Mathieu is going to talk about next if he makes it. But I do have a lot of overlap with his ideas, because his ideas have been very seminal in this area. So so you're going to hear some of this perhaps twice, because I wanted to try to tell at least a reasonably complete story. So the work I'm going to talk about is not all work that I've been involved with, because again, I thought it was good to give you a more complete story of the field. But of the work that I've been involved with, many people have participated, and I've tried to put in bold the ones who are here. I guess Mathieu is not here yet, but Marco, Daniel, and Sean are all here. And at least Daniel and Sean will be giving posters on work that I will touch upon here. And I don't know if Marco is giving a poster on the work that his work that I'm talking about here too. Okay, so you have probably all seen this diagram, right? Or maybe something like this. The idea being that until recently, right, the only way that we had to approach the glass transition to glass was to start with the equilibrium liquid. That was the only solid starting point we have. And the exciting thing, that the reason why we're all here in this room right now, is because of these developments at d equals infinity, which I guess you heard many of you heard a tutorial last June about from Jorge, but also this work that's been done on jamming and the unification of these two. So this is what I'm going to talk about. What I'm going to try to show you today is that I feel that we really have a pretty good handle on what happens at zero temperature in dimensions greater than or equal to 2, and that's our starting point here. So why has this been our starting point? Let me just first start by saying something about that. Why are we so focused on zero temperature, this very simple problem? And the reason why is for many years, Sid Nagel and I have been obsessed by this question of, is there an opposite pole to the crystal, right? And that's because, right, the perfect crystal is not something that exists even in principle except at zero temperature. And yet we study it. I mean, I'm going to start teaching it on Thursday. Another semester-long course on the properties of the perfect crystal, right? And that's because the behavior of the crystal, in many ways, many behaviors are universal and also very robust. Okay, and it's an extreme limit. And so the question was, is there an opposite limit? Is there a limit that we could call the anti-crystal? And that's what we've been focused on for more years than I want to admit. So, so why is this a useful question? And the reason why is because you really can't get to the properties of a glass by just adding defects gradually to a crystal, right? And and what are these properties? And the reason why is because the properties of glasses are qualitatively different from those of crystals, and they are also universal to all glasses. So that says that there's something worth understanding, okay? And what are these features? Many of them we still don't really understand, although they're phenomenological ideas. But for example, if you look at the low temperature properties of glasses, right, the heat capacity, if you divide by the heat capacity for a crystal, goes like T cubed, right? So this is heat capacity over T cubed as a function of temperature, and that's the phonon contribution to the specific heat that we know so well. For glasses, it goes like 1 over T, okay? And that is understood in terms of two-level system phenomenology, but, you know, how understood is that? I would say not very well, because we don't even know what a two-level system is physically, okay? Then at somewhat higher temperatures, there's this peak here, which is called the boson peak, a pileup of states that are far in excess of what you would expect from Debye. If you look at the thermal conductivity, for crystals, it goes like T cubed, and it's non-monotonic. For glasses, it's monotonic, and it goes like T squared, okay? And there's this little plateau here at intermediate temperatures. And this is very general, okay? So here are many different glasses. This is very old data from the 1980s or 1970s, you know, showing the same sort of features and the heat capacity and the thermal conductivity for many different systems. Okay, so so these are some examples of the common behaviors. There are many others, okay, but these have been the ones that have really sent us off on this pursuit. Okay, so another reason why we have been interested in studying the anticrystal, or studying the opposite limit to the crystal at 0 temperature, is to say, well, maybe if we want to understand the glass transition, perhaps it would be helpful to understand the glass a little better, okay? And this anticrystal really provides a way, very general way of thinking about problems with rough energy landscapes where you have a huge number of local minima. Okay, so so we're going to stick at 0 temperature through almost for the most of this talk until the end, okay? And then which means that we're always looking at energy minima, okay, and the properties of energy minima. And as I said, these are rough landscapes, so there are many, many of these. There are an e to the n number of minima, and so we're going to be looking at the properties of those. Now, we're going to look at them for a very special class of potentials. Okay, so these are particles that don't interact if they don't overlap, but unlike hard spheres, they are allowed to overlap, and the amount of the energy cost of the overlap increases with the amount of overlap with some power. And this power alpha, we vary between 2 and up. 2 would be a harmonic repulsion. 5/2 would be the Hertzian repulsion between elastic particles. And it's useful just to keep that to see what depends on alpha and what doesn't. Although nowadays we understand that so well, we don't really need to do that. Okay, so the idea is we're just going to start with some initial configuration. And there are various ways that you can, different kinds of classes of initial configurations you can start with. Let's not go into that at the moment. I'll get to that later. And then we're going to just, so this is a state where we put down the particles completely at random, okay? And they could be all the same size, or they could be different size. They could be monodisperse, bidisperse, polydisperse. Okay, this system happens to be bidisperse. Okay, then you quench it down to 0 temperature. In other words, you just plunge it into the nearest local energy minimum, and you look at it. If it's at low enough density, then it can find a state where none of them overlap. If it's at a high enough density, then you have these unavoidable overlaps between the particles, and you have forces, repulsive forces, these are these red lines, that are pushing them apart, and the thickness of the red line just tells you how big the force is, okay? Now, as I said, we have an extensive entropy of these energy minima, and we now know that in infinite dimensions, the landscape is actually fractal. So we're looking at the properties of these huge numbers of minima. We're just randomly sampling them. And the thing is that if every minimum had totally different properties, we'd be deeply in trouble. In other words, every time you prepared a different sample of a glass, you would get a different answer, for example, for the heat capacity or something. That's not the case, right? These properties, like the scalings I was telling you, heat capacity going like linearly in temperature, are quite robust. Not totally robust to the way they're prepared, but quite robust. And that tells us that the properties of these minima are in some ways deeply similar. Okay, and that's what we're looking at. Okay, what are the similarities and differences of the different minima, and what we're particularly interested are the statistics of these minima. Okay, and what I'm going to show you is different minima really do have these similar properties, and the averages and distributions of Bay power law scaling, they depend on the distance from the jamming transition that I'm going to show you next. Okay. So the jamming transition actually coincides with the onset of overlap, which is not obvious. Okay, so just before the onset of overlap, we have no particles. Just above, you have, it turns out that you have a ZC, a non-zero number of overlapping neighbors per particle. So you immediately jump from no overlaps to dense network of overlaps. Okay. And that value that you jump to happens to be twice the dimensionality, okay, in the infinite system limit. And that's a special number that's called the isostatic number, okay. And the way to see that is you go above and you creep down and you see that it approaches a constant as a power law, so you can pull out that constant quite accurately. Okay, so what's the significance of the isostatic number? This goes back to Maxwell. And the idea is if you have frictionless particles, n of them in d dimensions, and you want your system to be mechanically stable, you have to constrain all the degrees of freedom. So there are nd of those. And the constraints that you have are given by the number of interactions between the overlaps between the particles, the forces, right, between the particles. And that's n times the number of overlapping neighbors divided by 2. And so you can see that it's possible to constrain all the degrees of freedom if z is greater than or equal to 2 over d. And the lovely thing about spheres is, and there are arguments for this, that the sphere packings have exactly the minimum number of contacts that you need for mechanical stability at the onset of overlap. Now, is that enough, actually, to give you mechanical stability? And it turns out yes. It turns out that the onset of overlap does coincide with the onset of a shear modulus, okay, a non-zero Vulcan shear moduli. So here's a picture of the pressure as a function of how far you are from this onset of overlap phi c, and here it's raised to the alpha minus 1 power. And this is obvious because we have a potential that goes like the overlap to the alpha. So you differentiate it once, you get the force. That tells you the scaling of the pressure, so that goes like alpha minus 1. Okay. And that tells you that the bulk modulus must go like the phi minus phi c, the alpha minus 2 power. Okay. But if you look at the shear modulus, it has a different scaling. It goes like phi minus phi c to the alpha minus 1.5. Okay. Now, these scalings depend on alpha, right? And from now on, I'm going to just take alpha out of the problem. All right. So from everything that I'm going to talk about, I'm just going to remove alpha from the problem, because it turns out that all you need to do is introduce an effective spring constant. So if alpha equals 2, you have harmonic repulsions. Then you just have springs, right? Uniform spring constant, which tells you the repulsive force, the magnitude of the repulsive force between the particles. If you have some other potential, that just modifies the spring constant. So now you have a spring constant that depends on the amount of overlap. If you just put all your quantities, pressure, bulk modulus, just make them dimensionless using that effective spring constant, okay, then we remove all the alpha dependence from the problem. So that's the only dependence that this problem has on the potential. Okay, once you've done that, you've completely removed the potential dependence, and now everything looks the same as it does for harmonic springs. Okay, and that's what I'm going to do for the rest of this talk. Okay, those are units I'm using. Okay, so so as I told you, right, for sphere packings, right at the onset of jamming, you have exactly the number of contacts that you need, the minimum number that you need for mechanical stability. That means if you take one away, the system goes unstable. Okay, and that implies a diverging length scale, and this was first insight by Mathieu. Okay. That this would lead to a diverging length scale and also a vanishing frequency scale. So let me first go through the diverging length scale argument. Okay. So the point is that, so if we do this carefully, okay, what we're going to do now is we're going to take a system which could be above the onset of jamming. So I have more contacts than I actually need, because remember, the more I compress it, the more contacts I get. It increases as a power law above the isostatic value. Okay, so now I'm above jamming, and so I have extra contacts in the bulk beyond what I need for stability, but now I'm going to cut around the edge. I'm going to cut this out. Okay, let me first, just so that I don't cause confusion, let me explain what I mean by cutting this out. Remember, we only have repulsive interactions between the particles, so in order to keep them at this overlap, I have to be applying a confining pressure. So now how do you cut it? The idea is that you turn it into a disordered network. Okay, so, and I will be going back and forth between jam packings and these networks, but I will try to indicate very clearly when I'm doing what. Okay, so this is a trick that was also introduced by Mathieu. So you take these jam packings, at the center of each particle you put a node, and in between each pair of overlapping neighbors you put a spring. Okay, and you put a spring that is at its equilibrium length. So the spring is completely happy, so that you remove all the stresses. Because remember, really it's, if I have, for example, harmonic repulsions and they're overlapping, these are compressed springs, but I get rid of that, okay? So I get rid of all the forces on the spring, so I'm just left with this happy network of springs, okay? And if you look at the properties of the network, it turns out that it has the same scalings as the bulk and shear moduli, which is what I just showed you, that the bulk modulus actually jumps from 0 to a constant value at the transition, and the shear modulus increases continuously. Okay, that's what we see for the jam packings, and the networks show the same behavior. Okay, there are many other things that show this as well. Okay, so all right, so now, so we turn our jam packing into a network, we cut the network, and now we look at the rigidity of this piece of network that we have that has free edges. Okay. So the system is rigid, so I'm just rewriting the constraint of rigidity again, the Maxwell constraint. If the number of contacts or overlaps I have minus d times n is greater than or equal to, and before I had 0, now I'm being a little bit more precise, and that's just to explain something later. We have always free translations and rotations of the system. Okay, so those always remain 0 modes. Okay, so if we don't have to constrain those. Okay, so that's why this has to be greater than or equal to minus the number of that, because those are the ones that are never constrained, and we don't want to constrain them. Okay, so by NC, what do I mean? It's 1/2 times Z times the number, the number of contacts I have minus the number in the bulk, and the bulk contacts, the total number of nodes I have minus the ones that are at the boundary, and then I have some average coordination average number of neighbors that I have at the boundaries, which is smaller, okay, times the number of contacts, number of nodes that are on the boundary, okay? And then if you just work out this condition, okay, what you can show, you can put a bound on this, and you can show that it's rigid if the length scale is greater than some quantity here, which goes like 1 over z minus the isostatic value, okay? And it turns out then if you want it, since this has to be greater than this, what you want is the smallest possible value of this, and that corresponds to, that ends up giving you a length scale, L star, and we can put an upper bound on that, which just goes like this. So it's just some number divided by the number of contacts, okay? So this is just coming from counting. The idea is I've lost contacts at the boundaries, okay? So I have fewer contacts at the boundaries, but I have extra ones in the bulk, and those can balance, okay? And that balance ends up giving me a length scale that goes like 1 over the excess number of contacts. But at the jamming transition, z goes to 2d from above, and so this length scale diverges, all right? So let me just show you then, we're going to take this system, we're going to cut it. And so what I'm showing you here is here are the nodes of my network, okay, which correspond, you can think in the jam packing to the particles. What the blue ones are the ones that are involved in zero frequency modes, okay? So and whereas the red ones are part of the rigid cluster, okay? So what you see is the rigid cluster is somewhat smaller than the box that you cut. Okay, so here's my box that I cut. And now what I'm going to do is I'm going to look at this red cluster, this red rigid cluster that I get, and I'm going to make smaller and smaller cuts. Okay, so I'm going to cut smaller and smaller systems out of it. And you see at some point, there's a point where that large rigid cluster just goes away, vanishes, okay? And after that, I'm just left with really tiny clusters, okay? The upper bound, so if I look at the size of that rigid region, that size of that red cluster, okay, as a function of how many contacts that I had in my original system before I cut it above isostaticity, okay, I see that that length scale, I'm going to call that L star, diverges as I approach the jamming transition exactly as that argument would say, and it's actually not too far from that upper bound. Where do those little tiny clusters come from? It turns out that those little tiny clusters come from this term here, that because there are these free translations, free zero modes, that gives you another possibility of satisfying the inequality, which can be satisfied for very tiny clusters. Okay, so that's really a finite size effect, but that's there too. Okay, so that large rigid cluster. So what is this saying? This is saying that if I'm far away from the jamming transition, okay, I can make small clusters that are still rigid, that have free boundaries. But as I get closer and closer to the jamming transition and I lose my contacts, okay, my cluster has to be bigger and bigger in order for it to be rigid, because it has these free boundaries, okay, that tend to destabilize it. So that's what this is saying. So that's why the size of the rigid cluster must diverge as I approach the jamming transition from above. So that's one of our length scales. But there's another one, okay? There's another way in which marginal stability leads to diverging length scale. And this is, so I can think we're working with particle packings which have periodic boundary conditions. But another way to think of it is I have an infinite crystal, okay, with a very complicated unit cell. And I can look at the modes, the vibrational modes of that infinite crystal, right? And I can get a dispersion relation, okay? It turns out that we can make systems that appear to be rigid if I look at a single unit cell, but if I look at the infinite crystal, their dispersion relation can be negative at some wave vector which is beyond the unit cell. Okay? And so if we say, well, the system should really be stable at all wave vectors in the Brillouin zone, we want this whole periodic crystal to be stable, then that actually gives another length scale that your system has to be bigger than a length scale which diverges, okay, with a different power. So the first one diverged as 1 over z minus zc, which goes like 1 over the square root of phi minus phi c, or the packing fraction minus the packing fraction at jamming. This one, this one goes like 1 over delta phi to the 1/4 power, which corresponds to 1 over the square root of delta z, 1 over the square root of the number of contacts minus the isostatic number. Okay? Yeah.
These plots are constructed using the procedure that you described in the previous slide.
Yes.
So you take a big system with a lot of repetitions of the initial one.
We just treat it like we can do that analytical. Yeah.
Please repeat the question. I don't think it was
Yes.
clear.
So the question is, did we take a unit cell and then repeat it several times and then do the calculation on that? We just did the calculation on the infinite system, right? So we just calculate the dispersion relation of the infinite system with this complicated unit cell. Okay, and then checked and said, okay, is it stable at all wave vectors k or not?
And the fraction is over what? So you take many systems, you take many...
We take many configurations, many different unit cells, basically, many different jam packings. Okay? So that's a second stability length scale. And you can think of this as this is stable to perturbations at the boundary that are not as extreme as cutting, but that do not obey the periodic boundary condition. Okay, because they're on length scales that are greater than a unit cell. Okay. I'm just going to mention a current puzzle since Daniel Hexner is here and will be giving a poster on this. There's actually a third diverging length scale that we don't understand at all, and I'm just going to bring it up there just to confuse everybody because misery loves company. So the idea is the following. Suppose we apply a sinusoidal force at some wave vector q0 to a jam packing, and we look at the energy cost of that. Okay? Then you can write the energy as bulk modulus, which is a function of the wave vector q and g of q, okay, times the longitudinal component of the displacement, okay, and then the shear modulus times q squared times the transverse part squared, okay, plus the work done by this force, okay. And if you look at these, so this gives you basically the bulk of shear moduli as a function of q. So at 0q, they must approach what we had before. So the bulk modulus must scale like a constant. As we go to the geometry, this approaches a constant where the shear modulus goes to 0, okay, linearly with delta z. And indeed, if we take the bulk modulus as a function of q, okay, it is constant, okay, but then it bends over at some value of q, okay, and so that specifies a length scale. Now, what we've done here, what Daniel has done, I should say, is to collapse these things. And you see that this gives you q times delta z to the roughly minus 0.67. Okay? So that's another length scale. That's saying that there's a length scale that goes like delta z to the minus 0.67. So I've shown you two so far. One went like delta z to the minus 1. That's the cutting length scale. The second one was the infinite crystal length scale. And that went like delta z to the minus 1/2. And now we have one in the middle, delta z to the minus 0.67. Okay, we still don't understand this. And then what you have here is you have a crossover. So what it's saying is that on length scales that are long enough, okay, you recover ordinary elasticity theory with a bulk modulus that is constant at the jamming transition. Okay. On length scales that are shorter, though, you cross over to different behavior. This is jamming physics, okay? And of course, as I get closer and closer to the jamming transition, I have to go to longer and longer length scales before I recover ordinary elasticity. Okay. Interesting thing is if I look at the shear modulus as a function of Q, that does scale roughly linearly with delta Z, okay, as we expected at 0Q, at low Q, but it's actually independent of Q. So the transverse fluctuations are very well described. The transverse response is very well described by shear modulus, which is the same at all Q. So this is something that, okay, so we don't understand this, but it's telling us, I think, something important about the nature of the jam state here. Okay. And the crossover from ordinary elasticity to jamming physics, which you will see over and over again in this talk. All right, in fact, you're going to see it right now. Okay, so I just talked about the macroscopic linear response, or the linear response at Q equals 0, and the static response at some non-zero Q. But now we can look at the frequency-dependent response, right? So we can look at the vibrational modes of this thing. And so let me again remind you of our friend the crystal. Okay, the crystal, all crystals look alike. Okay, all the vibrations of all crystals look alike at low temperature or low frequency, and that's because the density of states, for example, always the density of vibrational modes always scales like omega to the d minus 1. The heat capacity always scales like t to the d in d dimensions. And the reason why is because the low frequency excitations are sound modes, and at low frequencies, okay, those sound modes have long wavelengths, and those long wavelengths average over all the details. And so basically that makes all crystalline solids look the same. Okay, and they don't care about defects. Okay, so this is an extremely robust result for all crystals. But now think about what we have, right? If we go close enough to the jamming transition, we've got these diverging length scales. So that says that no matter how long the wavelength of my sound wave gets, it cannot get longer than these length scales if I'm at the jamming transition. Okay, so there's something that's saying that that ordinary sound wave or Debye physics is cut off due to these diverging length scales, and there must be new physics coming in. What is that new physics? Okay, that new physics is that if you look at the density states for these jam systems, what you see is you have a lot of extra vibrational modes. Okay, I'm going to explain where they come from in a moment. They come, in fact, you can get them from the cutting argument. And so you have, and so what you have is the density of states, which if you're far above the jamming transition, okay, the density of states is fairly flat. And then as I go down in frequency, I suddenly realize, oh, I'm a solid. My density of states has to go to zero at zero frequency. Okay, I'm a happy solid. I'm stable. I cannot have any zero frequency modes that cost no energy. Okay. So this has to plunge down to zero. But if I get close to the jamming transition, I remain flatter for longer before I start plunging down, and so forth. So the closer I get to the jamming transition, the lower I have to go in frequency before I remember that, oh yes, actually I'm an elastic solid. I'm rigid, and so I have to go down to zero. And so at the jamming transition, it actually remains flat all the way down to zero frequency. Okay, and there's a frequency scale that's associated with where this peels off. If I look at that frequency scale, it scales like how far I am from the jamming transition to the 1/2 power, or it scales linearly with delta Z, the number of extra contacts. Okay. All right. So one thing I want to point out is that this frequency scale you can think of as coming from the length scales that I just showed you, or you could think of it the other way around, that this frequency scale spawns those length scales. Because once you, for example, if I have these frequency scales, I have two speeds of sound. Remember, I have a bulk modulus, which scales differently from my shear modulus. Okay. And it's because they scale differently, I have speeds of sound that scale differently. That gives me two different length scales. One corresponding to the longitudinal speed of sound, the bulk modulus, and the other one corresponding to the transverse speed of sound, which is the shear modulus. Okay? So, this frequency scale is actually tied in that way to the two length scales I showed you. Now, people refer to the boson peak. So what you do when you remember when I showed you the boson peak before, I showed you a plot of the heat capacity for all these different glasses, and I divided by T cubed. I divided by what you expect from Debye theory just for sound modes. And then there was this bump. I said, oh yeah, that's the boson peak. You can do the same thing with the density of states. You divide the density of states by what you'd expect from Debye theory, which is omega squared in 3 dimensions, and then you see a bump, okay, and you pull out the frequency at that maximum, and that's omega star. Okay, that's what scales like delta Z. Okay, and what this says is that, oh, there's a huge number of vibrational modes in excess of what we would have expected from sound modes, right? Why are they there? Well, they're there because there are all these lurking zero frequency modes. They're there because this system is close to marginal stability. So let me explain that argument. And I'm going to explain it rather carefully because recently it's been called into question, and I think it's actually fine. Okay, so all right. So the idea is we know that cutting the system can introduce, because I'm taking away contacts at the boundary, I'm reducing the total number of contacts. I can introduce zero frequency modes. Okay, modes that cost no energy. All right, so suppose the cut system has n soft modes, and that m of them are actually extended, so they stretch across the system. Okay, and where m is some fraction of n, okay, that does not go to zero in the thermodynamic limit. Okay, then the idea is we can use these extended soft modes as trial functions for the modes of the uncut system. And so then restoring, so we start out with the soft modes. So we start out with cut system modes, which are zero frequency modes. Now we go back to our original system, which had the periodic boundary conditions. Okay, so I need to restore the modes at the boundary. Okay, what's that going to, the bonds that are at the boundary that I had cut, I had to put them back. What that's going to do, that's going to raise the energy, right? And it's going to raise it if I assume, okay, it's a plane wave, omega should go like Q, okay? So then how much does it raise it? Restoring the bonds at the boundaries gives me, raises them to a frequency that goes like 1 over the size of the system, L, 1 over L, okay? And if you remember that animation I showed you where I was cutting at different length scales, remember what happened, that big red cluster suddenly vanished. It suddenly vanished because there was an extended soft mode that killed it. Okay. Before that, there were only localized soft modes that were blue around the edge. Okay. But once I cut a small enough thing, it went blue everywhere. Okay. In other words, this extended soft mode penetrated through that cluster, and that soft mode, that extended soft mode, appeared when the rigid thing was a size L star. Okay, so that tells me that I have no extended modes if L is bigger than L star. Okay, but I have extended soft modes if L is less than L star. Okay. All right. So then the point of the variational argument is says, well, at least m over 2 of the total number of modes in the system must have a frequency that is less than omega L. And so that tells me that the integral density states must obey this condition. But now recalling that m is 0 if L is greater than L star and non-zero if it's less than L star, you can rewrite it as the following. You see the density of state is omega L minus 1 over L star if L is greater than L star, and it's 0 if L, oops, sorry, this is backwards. This should be a less than sign, less than L star. Okay, and what that gives you is that if translating back, I'm going to now say, let's let omega star be 1 over L star. So L star scaled like 1 over delta Z, the excess number of contacts, omega star scales like delta Z, which is what we saw. Okay, then that tells you that the density states will be 0 up to omega star and a constant above it. Okay, so that's that plateau. That's that flat plateau in the density states. Okay. Recently, that's been called into question, okay, by 2 of my Penn colleagues, my former postdoc Daniel Sussman and Tom Lubinsky. So what they did was they prepared jam packings. They were exactly at isostaticity, so they had exactly 2D contacts with periodic boundary conditions. Then they cut them, and then they looked, and they found no extended zero modes, no soft modes, okay? But that animation I showed you, the thing with the blue and the red particles, right? The red rigid cluster, shows you that there's this rim of blue particles around. That there's this rim of. Let me just go show that to you. Just there. You see this blue rim. Okay. Now watch the blue rim as I cut it. It gets a little bigger, but it's not the same thing. It goes away. Okay. Okay. What that tells you is that the cutting length is a little smaller than you thought, okay? And what that translates into is that where you would expect to see extended soft modes appearing is not exactly at isostaticity, but a little bit below, a sub-extensive amount of below, so that when you take the thermodynamic limit, you still recover isostaticity Z equals 2D as where this all happens. Okay, but there's a sub-extensive delta to D minus 1. If you remove a sub-extensive number of contacts below isostaticity, you would find extended soft modes. So I think actually the Mathieu's original argument is fine. Meanwhile, Mathieu and Eric, I see here, propose another argument, which seems it looked fine to me. Okay, that may be correct, but I think it may not actually be necessary for this. Okay. Yeah.
But there was also some numerical work from Mathieu and Dan Lerner, where they prepared isostatic systems and cut one contact and found soft modes. Right. So how?
Yes, but they're localized soft modes. So you cut it, you get a soft mode, but it can be localized. That's the danger. So in order for the cutting argument to work, you must have an extended one. So we have plenty of localized soft modes. Those correspond to where the blue things are. Okay.
I remember in the paper there were two. They had both of them, the localized and extended.
In the original paper?
It's a paper of 2013, or I mean, not in the original one, in a recent one.
Okay, because the original one, Leo Silbert's calculations, it did look like there were extended soft modes exactly at isostaticity. Okay, so I didn't see, I'm not sure of this. I know Daniel Sussman then checked and was exactly at isostaticity, clearly did not see it going to 0 there. Okay, did not see extended soft modes. So, all right. All right. So let me just point out another thing about these systems. Of course, we know now, I've been telling you over and over again that the system is marginally stable right at the jamming transition. Right? It just barely has the number of contacts and needs to be stable. But in fact, it's marginally stable at any pressure, okay, or very close to marginally stable at any pressure. Okay, and again, we can get that from the cutting argument. So from the cutting argument, you have omega star squared goes like delta Z squared, or before I had omega star goes like delta Z. So the energy, if I take the square, that turns it into an energy, goes like delta Z squared. And if you remember in the harmonic approximation, if you have displacements of the particles, okay, the energy cost of it, there are two contributions. One comes from the second derivative of the potential, okay? That's longitudinal displacements, but then there's a contribution of transverse displacement that depends on the first derivative. Okay, now in the animation I showed you and all these arguments so far, we were working with these networks where we took the stresses away. Okay, what that meant was we took this term and we just set it equal to 0, and we were just looking at this term, and this term is what gave us delta z squared, a scaling that goes like delta z squared. So now we want to put this term back in and say, what does it do? Okay, well, remember, I have repulsive forces between these particles, and those tend to destabilize the system, right? It tends to want to buckle. If I have repulsive forces, then they tend to make the system buckle. Okay, so they tend to destabilize the system, and you see this is the force, right? It should scale like the pressure, so omega star squared has this delta z squared term from there here, but then this term gives you a negative contribution. It's destabilizing. It tends to lower the frequency and is proportional to p. Okay, and so if the system is marginally stable, so I said omega star equal to 0, then I get p going like delta z squared, which is exactly the scaling that we see, okay, for the jamming transition. And in fact, if you estimate these two terms, go back to this and estimate them quite carefully, you see that they come very close to canceling. Okay, so the system is actually nearly marginally stable at every pressure. Okay, sorry. So now let me talk about what do these modes look like. Okay, we have a density of states, which has a plateau region. This looks a little different. It's on a linear scale, but on a linear scale, this would look quite, on a log scale, this would look quite flat. Okay, it drops off at the high frequency end, and it drops off at the low frequency end. Okay, it drops off at omega star, approximately at the low frequency end. Okay, so let's look at what these modes look like. Okay, so it turns out that below omega star, below that boson peak frequency, okay, they look quasi-localized. So a few particles have very large displacement. They tend to be clustered together. And then there's this sort of swirly background, which is really a plane wave background. Okay, another way to think about what these modes are is suppose you send in sound waves. They would scatter off the disorder. Okay, and what would you see? Okay, you would see these modes, right? Another way to say it is that what are they scattering off of? They're scattering off some sorts of defects that are very good at scattering sound modes. Okay, those defects look like they're localized. Okay, and they're interacting with each other via long-range elastic interactions. Those are these phonons, these plane waves that are the background here. Okay, so we have quasi-localized modes at below the boson peak. If I look at the modes in the boson peak, okay, that's here. Okay, what do they look like? These are this often called the anomalous modes. They're extended and they're very disordered. They don't look plane wave-like at all. Okay, they're just a mess. Okay, and then at the very high end, they become localized again. That's Anderson localization. Okay, so what do these? I'm going to look at the modes of the boson peak. What are these modes like? What can we say about them? Okay, so so I can look at the structure factor of these modes. Okay, and what you see is that if I'm at low frequency, they're nice and sharply peaked. So if I had phonons, they would be sharply peaked at the wave vector, which corresponds to omega equals CQ, right? Omega equals speed of sound times Q. If I had sound modes, they'd be sharply peaked at a single Q, okay? What you see is that at low frequency, they are quite sharply peaked around, that Q, so we recover sound modes at low frequencies, okay? But if I'm at higher frequencies in the boson peak, I lose, it all gets smeared out, okay? So I lose this huge peak here, okay? And if you look at what you see that for a given mode, they're wave vectors over a whole range of Q, okay, that are contributing to the mode. And in fact, well, I don't have to go into that. Okay, there are many different wave vectors that contribute to this mode, okay? We know a little bit more about that, but you don't have to know that. Okay, so, all right, so now what are the consequences of these modes, having modes that look like this? Okay, these extended disordered modes. It turns out that that has huge consequences for the thermal conductivity. So imagine that we have a system where, you know, we're looking at the thermal conductivity. It turns out that you can, you know, with the Kubo relation, you can calculate the thermal conductivity in terms of the heat carried by each mode and the diffusivity of each mode, and that's, you have a matrix element here for how much energy a given mode, how effective a given mode is at transporting this energy. Okay, and there's this weird thing, right? That, as I said, the crystal goes up, okay, and then it comes back down, basically because phonons are scattering off the boundaries. Cattell, back in 1949, had this idea, oh, you know, there's this plateau here, and maybe the fact that it keeps going up after the plateau is due to there being a regime where there's a frequency-independent diffusivity. Okay, so he made this guess in 1949. And it turns out from jamming, we can confirm that he was right. Okay, so we can calculate this diffusivity, and what you see is, indeed, it looks like that. So here's what the diffusivity looks like. Let me look at it first close to the jamming transition. Okay, so the diffusivity at low frequency goes up. These are the sound modes. Sound modes are very effective, right? They carry energy ballistically. Okay, but then it hits this plateau where the diffusivity is small and constant over a large frequency range. If I now go a little further above the jamming transition, okay, I have my sound modes up to a higher frequency, and then it flattens out. Okay? And if you just do a simple calculation where you say, okay, well, okay, I have sound modes, okay, and above here I'm going to say I have some diffusivity, D0, which is the speed of sound times the mean free path. And I look at where the wavelength of sound, okay, is equal to the mean free path. What frequency is that? It's exactly the boson peak frequency. Okay, so below the boson peak, I have some plane waves that can carry the sound. Okay, but above the boson peak, I have those extended disordered modes, and those are extremely ineffective at transporting energy. Okay, and have this very flat diffusivity. What does that give you? Well, we know what that gives you just from Cattell's 1949 calculation. It gives you a thermal conductivity that rises linearly above the boson peak. Okay, so and the nice thing about the jamming transition, nobody could tell whether Cattell was actually right. Okay, but the nice thing about the jamming transition is that we can make this regime of frequency-independent diffusivity as big as we want, over as big a frequency range as we want, just by tuning our distance from the jamming transition. Okay, and one consequence that comes out of this is that this is tied clearly to the boson peak. This regime of frequency-independent diffusivity occurs above the boson peak, and so if I translate that to temperature, here's the boson peak in the heat capacity. The end of the plateau of the thermal conductivity, where it starts to rise again, should be at the same temperature, and indeed it is. Okay, here 10 degrees, 10 degrees. And in fact, for all these different systems, the onset, the end of the plateau corresponds to the boson peak, and that's not a coincidence. These two things are tied together. Okay, that's what we learn from jamming. Okay, so all right. So that's one nice way to look at the boson peak. It's the jamming, sort of canonical jamming picture of the boson peak. I wanted to just say that there are other ways of thinking about the boson peak, and I think it's important to sort out which features that I've told you so far are more general than jamming and which ones are specific to jamming. Okay, so remember, as I said, we can turn our jam packings into networks. Okay, and if I look at the dynamical matrix of this network, okay, it's a sparse matrix, and there's a lot of disorder in it because these are disordered packings, okay, that turned into disordered networks, okay, and they had the same scaling. Now I can show you that they have very similar density states. So if I take the spring network, that's the solid lines. That the density states for the spring network is the solid lines. The density states for the original jam packing are the dashed lines. Okay, why do the modes go to lower frequency if I include the stresses? It's that marginal stability argument I showed you, that the V prime term, the pressure or the forces tend to destabilize the modes. Okay, they shift the modes downwards. Okay, so you get modes leaking down to lower frequencies. And so that's why the original jam packing has modes extending to lower frequencies than this unstressed network. Okay. So if I look now, let me look at these modes. Okay. And again, I'm going to look at the modes of the boson peak. It turns out I want to now say, how can I understand the properties of these modes in terms of a random matrix ensemble, because they come from a dynamical matrix, which is a disordered matrix. Okay, so the idea is the following. So there's the simplest random matrix ensemble, the Gaussian orthogonal ensemble. Just choose your matrix elements from Gaussian distribution, essentially. That describes the eigenvalue statistics for jam systems quite well, okay? But what this plot shows is that it does not actually fit the eigenvector statistics well. So here, what we're doing is we're calculating the distribution of the lengths of the polarization vectors of the modes. So each mode, I have particle displacements within that mode, and I can look at the magnitude of that particle displacement and look at the distribution of those magnitudes, okay? Turns out that that distribution is the same for all the modes in the boson peak. Okay? And I'm plotting here the cumulative distribution. And here I have the red and the green are jammed packing. Okay, are from these networks, the spring networks from jam packings. Two different modes from the boson peak. Okay, and they are noticeably different from this dotted blue one, which is the Gaussian orthogonal ensemble, but they fit quite well to the black dashed one, which is a different random matrix ensemble. And what's the difference between them? We call this the boson peak ensemble. The difference between them is it's very simple. The idea is that just from translational invariance, if I look at the dynamical matrix of this system, right? You constructed it just, I'm sure you've all done this for phonons, right, and crystals. You see that the diagonal term has to be minus the sum of the off-diagonal terms in the same row. Okay, there's a sum rule for each row. Okay, so random matrices that satisfy this constraint, okay, have boson peaks with the right eigenvector statistics, with exactly the ones that we see for jam packings. In fact, you don't even have to satisfy that sum rule exactly. You can just satisfy it statistically. So for example, if the off-diagonal elements are chosen from a Gaussian distribution, the on-diagonal elements have to be chosen from a Gaussian distribution with a bigger variance, with a variance that's bigger by the number of non-zero terms in the row. Okay? And as long as you satisfy that constraint statistically, that's enough to give you this, the right eigenvector statistics. So when you look at it this way, then you say, okay, well, the boson peak is actually just a consequence of having disorder, a random matrix, okay, plus translational invariance. That's all. Okay, and in fact, a good way to define the boson peak, why define it in terms of dividing by Debye? That's only good for systems that actually have sound modes. Random matrices don't have sound modes necessarily. Why not just define them in terms of their eigenvector statistics? The boson peak is where the eigenvectors have these particular statistics. Okay. What's so interesting about that? Well, the point is that I can make these matrices that are not sparse, right? I could populate every term in the matrix and get the right statistics. But I can also make these matrices sparse. Okay, so I can make them sparse so that I have Z contacts per particle effectively, or Z non-zero or zero non-zero entries per row, or Z over 2 non-zero, whatever. They have to be symmetric. You have to make them symmetric, and enforce the sum rule, and then they're positive definite. And when you do that, what you see is that the random matrix ensemble, if you decrease Z, okay, it has a boson peak frequency that scales like Z minus ZC. Okay, so you recover the scaling of omega star going like delta Z just in these random matrix ensembles without any jamming physics at all. Okay, without special jamming physics, except for isostaticity. Now, in this case, we just, if a real dynamical matrix, if you're in higher dimensions because you have vectors, it has a certain submatrix structure. We didn't bother with that, and therefore our matrices effectively correspond to d equals 1, so ZC was equal to 2. Okay, but you can do this in any dimension you want and construct these, and you see that. But you see, okay, all right. So that's so the point is this scaling of omega star going like delta Z is more general just than jamming. Yeah.
How is the boson peak ensemble defined?
How's the boson peak what?
Ensemble.
Ensemble. It's basically random matrices where the off diagonal terms come from bounded distributions, okay, and are negative, and between 0 and some bounded negative number, and that the diagonal terms at least satisfy the sum rule statistically.
And you said that they have the property that the eigenvectors, the distribution of the eigenvector elements is universal?
The eigenvector distribution is universal. That's right.
The elements of meaning that the elements of
The distribution of the polarization vector magnitudes is universal. Okay. All right. Yeah.
When would be a good time to take maybe a 5-minute break?
Sure.
I mean, are you almost done with the random matrix discussion?
Yeah. Let me finish that, and then that's okay. Then that would be good. Okay. Okay. How long have I been going? An hour. Okay, good. All right. So another way to make random matrices is to construct dynamical matrices from real networks. Okay? But they don't have to be networks derived from jam packings. So an interesting thing was that if you take a jam packing, okay, and I turn it into a spring network, then the networks that I created from these jam packings have the right scaling, right? That the bulk modulus goes to a constant, the shear modulus goes to 0, so the ratio goes like delta Z, same as jamming. But if I take a network that was derived from a jam packing that was very far above the jamming transition, and now I cut the bonds randomly, okay, Wouter Ellenbroek and Martin Zorana Zaratra, Martin van Hecke, and Wim van Saarloos showed that you get a totally different scaling, that the bulk modulus and the shear modulus both go to 0, okay, so that the ratio remains constant, and that's actually rigidity percolation. So you can cut your networks in different ways, and you will get different matrices, right? Different random matrices coming from networks that you prune in different ways. And in fact, you can prune them to have any ratio of the shear modulus and the bulk modulus that you want. You don't have to have just jamming scaling, okay? I can prune the bonds that make the smallest difference when I take them away, make the smallest difference to the bulk modulus, and I get jamming scaling. But I can prune bonds that make the smallest difference to the shear modulus, okay? And then the ratio, what happens is that as I prune, the shear modulus doesn't drop very much, but the bulk modulus drops more, so the ratio goes up. Or I could take away the bonds that make the largest difference to the bulk modulus, okay? That makes the bulk modulus drop like a rock, so that the ratio of the shear to bulk modulus goes to infinity very rapidly, with a power law of about 9 in 3 dimensions. Or I could prune bonds that make the largest difference to shear modulus. Okay, I can prune them all in these different ways. Okay, so with that, what you see is that we can vary G over B by more than 20 orders of magnitude. Here, we're only messing with 2% of the bonds. So it's very efficient. We can change this ratio shear to bulk modulus, which is changing the Poisson ratio. So we can make negative Poisson ratio systems, which if you pull on them this way, they actually expand this way instead of shrinking. Okay? So you can do that. So the scaling of G over B is not robust, right? The scaling of G over B going like delta Z is special to jamming. And it's not, you don't get the same thing no matter which way you prune. You can get anything you want. Okay? But if I look at the density of states, okay, it turns out the scaling of omega star is quite robust. That no matter which way I prune, I still get omega star basically going like delta Z. Okay. These curves are collapsing at low frequency. You know, where they start to head down is about the same. When here I'm collapsing frequency, I'm dividing out by delta Z, and that's working pretty well in collapsing these curves. Okay, so that says that the scaling of omega star with delta Z really just depends on having a system that's, you know, that we're varying away from isostaticity, but doesn't depend on specific jamming physics beyond that. Okay, but the flat density states is something else again. Okay, the jamming case has a flat density of states, but you see, if I remove the bonds that contribute the most to the bulk modulus, as I remove more and more bonds, the density of states changes shape. It becomes less flat. So if I'm closer to isostaticity, it's definitely decreasing here. Same for removing the ones that contribute the most to shear modulus. If I remove them randomly, though, as I go closer to isostaticity, I'm going this way, and the density of states is actually increasing. And in the random matrix case, okay, it is decreasing. So it's not flat. So the flatness of the density of states seems to be special to jamming physics, but you don't see that really in the cutting argument. So I think there's still things to be understood here when you think about things carefully. All right, let me stop there, and let's take a break, and then I'll continue. Okay.
So take a 5-minute break. The restrooms are nearby.
Sorry, I got distracted a moment, and then
Yeah.
the W star, the
Yeah.
one that is H bar thing. There was one that.
Yeah.
What is it exactly? I'll tell you why afterwards.
So the one, so I just said
The-
H bar omega star equal to KT boson.
Yeah.
Yeah, for the KT where the heat capacity has a peak.
And
Heat
omega
capacity
star
over
is
T cubed
still
has a
the,
peak.
Is the place where,
And,
as usual.
and again, it's where the density of states drops off.
Let me tell you afterwards why. Are you staying till the last day?
No,
Ah,
because I'm teaching on Thursday. I have to leave Wednesday.
okay. But then I will have to tell you sometime.
Yeah,
Not
but
in.
not on Thursday.
Yeah.
Right. Yeah.
No, because H bar T, whatever, I'm taking it to the other side so that I have omega star on one side, is the famous bound on the Lyapunov exponent, which has the same dimensions as omega for any system. That's the fashionable thing.
Wait, which Lyapunov for what?
Of the system.
Oh, just of the system, for the dynamic.
Quantum dynamics doesn't
Quantum.
allow you to have a larger Lyapunov than that, and it's precisely the same number. So with a 2 pi, and I mean this is a bound that is absolutely general, so it's in particular true for this system.
I see.
So it's a bit intriguing.
That's interesting.
Yeah. So I'll.
Oh, let's definitely talk
let
about
me do
this.
the following. Let me send you my talk. Okay?
Okay.
The one you're going to miss.
Ah, okay.
You have a
Yes.
laptop at home.
Yeah,
you
yeah,
have
yeah.
At home, meaning in the
Yeah.
chair. So
Yeah.
at least when you're bored in somebody else's
Yeah, yeah, I
talk,
have my laptop. Yeah,
you can always have a look at it. so
that'll
that
be
you see.
great. Okay. All right. So and then we can talk
leaving
before
on
I leave.
Tuesday or-
I leave Wednesday morning.
Wednesday morning.
Yeah.
I'm talking Wednesday morning.
And that's when
I
you
guess
talk.
You will not come here.
Right. Because I have to catch my flight.
Okay. So let's meet sometime. They don't give us a
they don't give us a whole lot of
but
time, but
not
maybe
at all.
Tuesday. So if you
Maybe
can
Tuesday.
send me your
Wednesday I'm
talk.
supposed to talk, and with him I'm
You have your
well,
talk ready?
Yeah, of course.
Ah.
I'm that kind of person. Hola, ¿qué tal?
That's
I'm that-
okay.
I'm that kind
then
of
you can
person.
send it to me right away, and then I can look at it by then. Okay. Hi. How are you doing? Good to see you again.
Good to see you.
Yeah.
It's so good to have everything together.
Yeah.
I read the APL with Lisa, and I was understanding that you looked at the distribution of the norms of the eigenvectors.
The magnitudes. The
Yes,
magnitudes
yes.
of
So
the
L2
of
or
the
L1.
displaces. Oh, we looked, and then we compared the way we established whether things were universal was we compared the distributions to each other, and we used the L2 norm to do that. So I didn't show that, but that's how we decided whether two distributions were in the same universality class or not, is if their L2 norm was close to
I
zero.
see. But it's a distribution of the eigenvector magnitude.
Magnitudes. Yeah.
Okay, but that's what I remember also. But didn't you say here, you pointed in the real space of all the particles jammed that they were vibrating maybe, and the distribution of those displacements had also some significance? Right, just a
Yeah.
little bit earlier. What did you say about the distribution of the displacements in the jam state?
So in the jam state, the distribution displacements in the boson peak looks like the distribution that you get in these random matrix ensembles.
Of the
Of
elements.
this boson peak. It's the same.
Just an argument to invoke
Yeah.
the Gaussian.
It's not the Gaussian orthogonal ensemble. It doesn't fit that, but it fits another very wide class of random matrix ensembles. So it suggests that you can
Use random matrix theory.
use random matrix theory, and it suggests that you can define a universality class for random matrix ensembles based on the eigenvector statistics. I'm sharing the same eigenvector statistics.
Okay, so I guess in one sentence, the BPE
Yeah,
and the GOE
are
two
not the
universality
same.
classes.
The
Different.
GOE does not belong in the BPE class.
Okay, and they have different
universality
distribution
class.
of
And they have different
eigenvector.
eigenvector distributions. That's right.
Awesome.
Yeah.
Has anyone else, like when people do RMT in general, I've never seen anyone looking at the eigenvectors. Only the Wigner semicircle and
No,
other
they
pieces.
always look at the
Yes.
eigenvalues. This was
But
the
then
new
on-
thing, was to look at the eigenvectors. That was what was new about what we were
Yes.
doing.
Has anyone ever in the math community anywhere else? Have you ever seen anyone else?
No, that's
doing
very
distributions?
new. That's very new. Yeah.
That's what I thought.
Yeah.
But I didn't have much
Yeah,
experience. Okay.
yeah. Terence Tao had been looking at properties of eigenvectors, but as I understand it, he had not been looking at these distributions and classifying universality in terms of the distributions.
I thought this was very good, very smart.
Yeah, yeah. Thank you. Yeah.
I don't know how to make the dynamic matrix positive definite.
What?
I don't know how to make the dynamic matrix a positive definite with the random matrix.
Ah, yeah. So we described that in our paper, but yeah. So in general, a lot of the matrices we look at are not positive definite. and they do have negative squared eigenvalues. Okay, it's in fact it's symmetric around 0. Okay, but then they have a peak. They have this peak in the density
omega
of states.
square is positive, right? Omega square is positive. I mean,
For a lot of the matrices we're looking at, it's actually not positive. Not necessarily, and you have at positive eigenvalues you have a peak, and at negative eigenvalues you have another peak. It's symmetric around 0. Okay, a lot of the matrices that we look at, but you can construct positive definite matrices. Okay, what you need to do is choose the off diagonals to be negative and bounded. You need to satisfy the sum rule, and you need to make the whole thing symmetric. So they're these it's called diagonally dominant matrices. So mathematicians understand how to make random matrices that are positive
I
definite.
know you can factor the dynamic matrix with some dynamic matrix with some two part, and I don't know how to describe. I mean, you could factor the dynamic matrix with two part, like particle Hall symmetry,
Or yes, yes, you can do that. Yeah.
Another
Yeah.
question about I know one can do that for random dynamic matrix. You have if omega equal to 0, the density of state is omega.
Sorry, I think Francesco wants to talk, but let's talk afterwards. Yeah. Okay.
So you think 45 minutes is enough, or you want to?
Yeah, I'll just cut out some things.
You can have.
I'll just cut out things.
No,
Yeah,
it's fine.
it's fine.
Okay, so we
Yeah.
start again.
Okay, so in the last hour, I was telling you about, or more than an hour, I was telling you about the results. And if I sum up all the results, you see that we have a bunch of scalings here. And one thing I left off was omega star going like delta phi to the 1/2. Okay, I should have that on the list as well. Okay, so we have a bunch of different scalings. A number of these, in fact, these 3, I believe, these numbers actually agree with the infinite dimensional solution, which gives 1/2, 1, and 1/2 there. So that is great, right? But why do they agree with the infinite dimensional? Do they really agree with the infinite dimensional solution? Because these are calculated in 2 and 3 dimensions. We see basically numerically the same exponents in 2 or 3 dimensions. And you can say, okay, well, if I have numerically the same exponents, then maybe d equals 2 is the upper critical dimension. But looking at numerical values of exponents and trying to say if they're the same or not is a notoriously bad way of deciding whether you are above the upper critical dimension or not. Okay, so let me tell you just some of the reasons why we really do think that 2 dimensions is the upper critical dimension. First of all, and this is very hand-wavy, but there's an Emery-Ma type argument, okay, and it comes from the cutting argument. So the idea is, remember, we have a cutting argument where the number of soft modes, I introduce soft modes by cutting around the edges, so that's L to the d minus 1, but I have extra bonds in the bulk. Okay, it's like this L to d contribution, and I'm looking at the balance of these 2 terms, and that's what gives me L star going like 1 over delta z. Now, let's suppose we have fluctuations of the coordination number, and so those fluctuations go like L to the d minus d over 2, and if the fluctuations get too negative, then I can get soft modes from that, or too positive, I can get soft modes from that. So negative, yeah, I have the wrong sign here. But you can see that if I compare this term to this term, okay, this term is going to lose if d is greater than 2. These 2 terms are exactly equal in d equals 2, which suggests that the upper critical dimension is 2, okay? I actually think the strongest evidence that the upper critical dimension is 2 comes from the finite size scaling. So it turns out that for critical phase transitions, quantities like the magnetization or the susceptibility, anything you want to look at, if you do their finite size scaling, they collapse as a function of system size divided by the correlation length if you're below the upper critical dimension. But if you're above the upper critical dimension, it scales like system L to the D, or the total number of spins, okay? So the total number divided by the correlation length to the upper critical dimension, okay? So, so you get this difference that things always collapse with N, with L to the D, and not with L, okay, over some length scale. Okay, and that's exactly what we see. So this is just, for example, delta Z and G, the shear modulus. And you can see in 2D and 3D, they collapse very nicely with P to the 1/2 times N. And the fact that they collapse with N here and not L, okay, but with L to the D in both 2 and 3 dimensions is, I think, very strong evidence that the upper critical dimension is 2. Okay. So, all right. So that's why mean field theory, the D equals infinity solution, we think that's why it captures the exponents all the way down to D equals 2. Okay. Yeah.
But since you can't really define rigidity in one dimension,
Yeah. What does it mean?
it's 2, then
It's also the lower critical dimension or whatever. Yes. 2 is the only interesting dimension from a critical point of view. That's right. Yeah. The other thing I just wanted to say, I sort of swept this under the rug. I said there was some phi c, okay, that each different minimum, you know, I can look at a given minimum and see where things jam, and I was looking always as a function of where I am from relative to that jamming transition, but that jamming transition is different for each different configuration, okay? There's a distribution of jamming thresholds. So for a given way of preparing the states in a given system size, there's a distribution of jamming thresholds. But for a given way of preparing your states, the jamming transition is sharp in the thermodynamic limit. So as you take n going to infinity, all the jamming transitions thresholds are at the same place for a given way of preparing it, but different ways of preparing it will give different densities, volume fractions for the onset of jamming. And I think yeah. So just to say, so it appears that if you can avoid crystallization, jamming transition appears to be sharp as n goes to infinity for any given protocol. But it does depend on protocol, and this was shown by Ludovic and co-workers. This is wrong. That should be Chaudhary was the first author. Sastry was also on that paper. But anyway, the nice thing is that the critical scalings that I have shown you so far don't seem to depend on the protocol. Okay, so what I've shown you, all those scalings that I made such a big deal about are really robust. It's just that the critical density does. And the fact that the critical density depends on protocol is really consistent with the mean field picture that goes back to Jorge's work. This is a picture from Jorge's paper that just shows that different quench rates, for example, could give you different values of phi c. So there's a line of these. So there's actually what's called the J line, point J. The point J we call the jamming transition, but it's actually a line of these. Yeah?
So the distribution depends on system size.
Yes.
So which length scale is related to this finite size?
There's not a length scale. It just goes like the square root of n, sort of central limit theorem.
Position of the
Yes. So the peak position does shift with n. So the shift of the transition also could give you a length scale. So it's around 0.7. We don't know. It's been looked at very precisely by Peter Olsen and Steve Teitel. They try to look very carefully at that. It's around 0.7 or they say it could be, I mean, it's not pinned down very precisely. They work in 2 dimensions, so we believe that 2 dimensions is the upper critical dimension, so that they're log corrections, and that messes all, so that you don't see the, scaling collapses are not as nice in 2D perhaps because of these log corrections and so forth. So I'm not sure exactly how useful their very careful analysis is, but it does appear to be, if you say that's a different length scale, that is again a different length scale from the ones I was talking about before. Yeah, we've got just a overabundance of diverging length scales in this problem, and not really enough understanding of how they're all related. Okay, so all right, so what I want to go on now is to tie all these exponents together. Okay, so we have this nice list of exponents there. Great. I've got to get better with this thing. Okay, we got this nice list of exponents, and now what we want to do is to try to tie them all together with a scaling theory. Okay, and so we're going to make a scaling ansatz. And let me just remind you for the Ising model. Okay, for an equilibrium phase transition like an Ising model, you can write down a scaling ansatz for the free energy that looks like this. So it depends on the distance from the critical temperature, the reduced temperature, and the magnetic field, and, for example, system size. And you can write down a scaling ansatz for that. This is a state function, okay? And it's important that the system is in equilibrium, because then I can differentiate this and I can get, for example, I differentiate this respective field, magnetic field, I get the magnetization, okay? I differentiate twice the respective magnetic field, I get the susceptibility, etc. Okay? The jamming is a non-equilibrium transition, okay? And such transitions have often been collapsed. You can take data and you can collapse them. There are lots of non-equilibrium phase transitions where you can collapse data. Okay, but what I'm talking about is more than collapsing data. I'm talking about a scaling ansatz for a state function, and that has really just been restricted so far to equilibrium phase transition. And it turns out that jamming is really the only exception that we actually know of, where for a non-equilibrium transition, you can actually make a scaling ansatz for a state for thermodynamic quantity, in this case, the elastic energy density. Okay. So let me explain how that works. All right, so here's our scaling ansatz. It looks like this. So I'm going to say the energy depends on delta Z. Okay, so if I compare to the Ising model here has reduced temperature. What's going to play the role of the reduced temperature that tells me how far I am from the transition is delta Z. Okay. And there are reasons why we do that, which I can get into, because you could have also chosen pressure, which is often what we do numerically. We vary pressure, or you could have chosen phi minus phi C. Okay, it turns out that choosing delta Z makes things particularly elegant, and that it puts compressive and shear strain sort of on the same footing, so that delta phi now appears here. So now then, what's in place of these two fields? So here I have a magnetic field. Okay, as one of my relevant fields. In the jamming case, we have to introduce two. One is the compressive strain, or phi minus phi C, and the other one is the shear strain. Okay, and the reason why we have to introduce two is because the shear and the bulk moduli have different scalings. Okay, all right, and then here we have the system length, right? Times t to the nu, the system length divided by the correlation length in the Ising model. But remember, in the jamming, we're at or above the upper critical dimension. So we shouldn't use system length, we need to use n, the system number, okay, times delta Z to some exponent there, okay? So that is our scaling ansatz, all right? All right, did I want to say anything? I think that's all I wanted to say. All right, so now I've got this, there's my elastic energy, same thing again. And now I can start differentiating, right? Because if I differentiate the elastic energy with respect to the compressive strain, I get the pressure, right? if I differentiate the energy with elastic energy with respect to shear strain, I get the shear stress. Okay, if I differentiate twice with respect to the compressive strain, I get the bulk modulus. I differentiate twice with respect to the shear strain, I get the shear modulus. Okay, and so I can just go ahead and write these things down. Okay, and what you see is that you're going to get a bunch of scaling relations here. Okay, so so if you see what I have here, okay, I have 1, 2, 3, 4, 5, 6, 7, 8. I have 8 unknown exponents in here, okay? But I have 5 equations, right? The 5 equations are that these are related because they came from derivatives. The pressure was one derivative E with respect to delta phi, so this exponent is zeta minus beta phi, etc. So that cuts it down. So I have 8 exponents, but I have 4 scaling relations. So that cuts it down to 4 unknowns. Okay. All right. Now, there's another scaling relation, and I want to talk about it because there's some nice physics in it, which is, let's look at the stress tensor itself. Okay, so here's the shear stress, here's this whole stress tensor. The pressure is just related to the trace of that stress tensor, right? And then the shear stress is related to off-diagonal elements of that stress tensor. And the point is, in jamming, we do things isotrophically. We just create things at random, we quench down. Everything's isotropic, okay? And because things are isotropic, right, the off-diagonal elements add incoherently. They could be positive or negative, okay? And that gives me that S squared, the shear stress squared, has to go like the pressure squared. Its basic scale is set by the pressure squared, but it's divided by N, okay? Because it's fluctuating around 0. It's just some central limit theorem, okay? If you do that, you see that gives a relation for the exponents for the stress, the pressure, in terms of delta Z and N. Remember, all these come with specific scalings with delta Z. And that gives me an exponent relation, okay? And this exponent relation, the fact that S and P have these, that this factor of N comes in, that relating the magnitude of the shear stress fluctuations to the pressure. I've got this factor of N coming in, is why the shear and bulk moduli have different scalings, okay? If these two things were the same, if psi were 0, okay, if I didn't have that factor of N there, then the shear and the bulk moduli would have the same scaling. All right, so what we can do is we can take certain exponents either from the theory or, so we can take them from the cutting argument, for example. So that relates, for example, the pressure to delta Z. I said the pressure goes like delta Z squared. The finite size scaling exponent, we can make arguments for the bulk modulus. Or you could just take 3 of these from numerics, if you like. But once you take these 3, you can predict the rest, right? Because I have 8 unknowns and 5 scaling relations now. So I can fill in the rest. And that makes a new prediction for the scaling, for example, of the shear stress fluctuations of these states. So if I look at that, here's our data for that. And the prediction is they should collapse in a certain way, and that does indeed collapse the data. And it collapses the distribution of shear stresses as well. Okay, so here's our prediction, and that really is satisfied. Okay. All right. If we're actually in the upper critical dimension, okay, this finite size exponent must, in other words, whether I scale with L or N, it shouldn't matter if I'm in the upper critical dimension. In other words, I see scaling of N with delta Z. So this phi equals 1 says that N, I collapse N with delta Z. Okay, well that corresponds to L times delta Z to 1/2 squared. Okay, so that says that's L over C squared. And what is that length scale? That's our transverse length scale. That's the one that goes like 1/3 squared of delta Z. So it was not at all obvious that that scaling theory would work to describe this system because we have multiple diverging length scales. The whole point of scaling theory is that there's one important diverging length scale. And what this is telling us is that, yes, we do have those other length scales, but somehow the one important one is the transverse length scale, the one that goes like 1 over square root of delta z. Okay? And why that is, we don't understand. All right. So now, going to Marco's work, we can now prepare our states a different way. Suppose we prepare them by shearing them. So this has been shown that you could start with an unjammed configuration. This was first done with these photoelastic beads by Bob Behringer's group. Okay, these photoelastic beads, you shear them. Okay, they're not jammed, and you shear them, and you can get them to jam. So you're at a density below jamming, but now you shear them, and they can jam on you. Okay. What are the properties of that state? That's a different way of preparing jam states. Those jams, it's a way of preparing states that are now anisotropic instead of isotropic. Okay, and what that does is it changes the scaling relation. All right, it says s squared now should scale like p squared because it's isotropic. It can support a shear stress. Okay, because it's anisotropic. What that gives me is now that it predicts that the scaling, the exponent for the shear stress should be related to pressure. In other words, the pressure should just be proportional to the shear stress, and indeed it is. Okay, so it changes these scalings, and another consequence of it is, as I said, if s squared goes like p squared, if I don't have that factor of n, then the shear and the bulk modulus should scale the same way. And it does, they do. Okay, so the shear modulus now goes to a constant. Instead of going to 0 like delta z, it goes to a constant just like the bulk modulus. This is for shearing in the xy direction, but if I look at the shear modulus, the elastic constant in the xz direction, I see it goes to 0 like delta z, just like in the isotropic jamming case. Okay, so cxyxy, the elastic constant for the xy direction, changes and now goes to a constant instead of going to 0. So if you fill in this table, you can fill in this table that these exponents changed, and now I get different exponents from what I got for isotropic jamming. Say, oh my God, I prepared my state in a different way, and I get into a different universality class. I change all my exponents. Okay. It turns out that you can think about it in such a way to unify these two things. Okay, so in the infinite system size limit, a jam system prepared isotropically must have only 2 elastic constants, the shear and the bulk modulus, right? But for any finite system, it actually has 21 elastic constants in 3 dimensions and 6 in 2 dimensions. Okay. If we're in 3 dimensions, there are 21 elastic constants. You can map those elastic constants onto a 6 by 6 symmetric matrix that has 21 distinct elements in it. Okay? All right. And now you can look at that matrix, okay? And you can diagonalize it. Okay? It turns out that in that 6 by 6 space, okay, elastic constant space, there's one of the eigenvalues is constant at the transition, and the other 5 all scale like delta z. Okay, they scale together. One is way up here, it's constant. The other one scale like delta z. Okay, and in the case of isotropic jamming, that one is just the bulk modulus. Okay, the one that's constant is the bulk modulus, and the shear modulus and other elastic constants all scale like delta z. Okay, but in the shear jam case, I can do the same thing. I can construct this 6 by 6 matrix. I can diagonalize it, and again, there's just one eigenvalue that scales like a constant, and the other 5 scale like delta z. Okay, it's just that the eigenvector corresponding to this eigenvalue now projects not only onto the bulk modulus, but also onto cxyxy. Okay, so what this tells you is that it doesn't matter how, well, I'm generalizing now, speculating. Okay, we only have 2 ways of preparing it. But what this suggests is that it doesn't matter how you prepare your jam state. I could prepare with any combination of loading conditions, compression, shear, uniaxial, this. I could do anything complicated. And if I get it to jam, it should have this symmetry. It should have this SO3 symmetry associated with it in this 5-dimensional subspace. Okay? So we think that's the true symmetry of the jamming transition. Okay, and so the point is not that the bulk modulus, necessarily that the bulk modulus goes to a constant, the shear modulus goes to 0, but the point is that there's one eigenvalue of the elastic constant matrix, which is constant, and the other 5 go to 0 at the jamming transition, that's the real symmetry of the jamming transition. Okay, and if you think about it that way, the shear jamming and the isotropic jamming systems are actually in the same universality class. Okay, so what's so great about this? How am I doing on time? So many non-equilibrium phenomena, as I said, exhibit scaling class. So jamming is one that can be described by scaling onsets with a potential energy, and that's for a very simple reason. That's because all the non-equilibrium parts of aspects of the problem are captured by phi c. All the glassy physics is in, different ways of repairing states can give you different values of phi c. Okay, but once I've taken that out, okay, the rest of the physics is essentially equilibrium physics. Okay, and that's why scaling ansatz is possible. So there's really a clear separation between the glassy and the jamming aspects of the problem. Okay. Now, the next thing is we know that if there's a scaling ansatz, then RG should be possible, okay? And then we know that. And I was going to tell you, let's see. Hold on, let me just look at my talk. What else was I going to say? I can't remember. I'm so blitzed by this point, I have no idea what I was going to say next. Oh yeah, I'm going to skip that because it's in Sean's poster. Okay, so please go and see Sean's poster. We have developed a way to do RG, a real space RG, and it does give collapse of the boson peak frequency. Okay. All right, so please see Sean's poster. All right, but why do we care about RG? I mean, you know, say we're at or above the upper critical dimension. Mean field theory is fine. Who cares about RG? Okay, but the point is that RG is not just a way of getting exponents. It's a way of understanding universality. And we've left out a huge number of things. We've been looking at this stupid model of spheres, you know, with this special potential, no friction, no anything. Okay, in fact, I remember I was hiking. We hired a guide to go up to a peak in the Canadian Rockies, and we were talking. It turns out he's an avalanche consultant when it's not time to either ski guide or hike or climbing guide, and so he goes around the world consulting on avalanches and advising people on avalanche dangers, and he says, oh yeah, it's all about the stresses and strains and the snowpack. And I said, oh yeah, I think about that too. And then I said, except that, well, for me, snow is made out of spheres, and there's no friction in gravity. And there's this long pause. And I realized that he was thinking, I'm bringing a crazy woman up this peak. And finally he said very, very gently, well, friction and gravity are kind of important. Okay, so the point is that real systems have all of these effects that are not included. And now, if we have this RG way of doing things, we can see how those effects, what the RG flows look like, and how those effects change the behaviors that we see in jamming. So it gives us a way to understand how much of the commonalities that are shown by all these very, very different systems, granular packings, metallic, organic, inorganic glasses, colloidal glasses, they all look, there are many things that look the same, and this provides a way of telling us. Okay, that's why RG is good for that. Okay, I just want to quickly go back to the crystal, which is where my starting point. I said we wanted the anti-crystal. right? And if you think about now, let's think about this crystal. And I'm sticking with my same old potential, okay? So let me create a crystal, a perfect FCC crystal. That is the ground state for that potential, okay? Let me create it, for example, at some high density so that our spheres are overlapping. It's still the ground state. Now, let me decompress until the spheres are just touching. What will happen? The shear modulus remains absolutely constant until they just touch, and then it drops to 0. So the shear modulus is discontinuous for the crystal, okay?